Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So today we will be solving DP16, and the prerequisite to this DP16 is you must have seen the DP14, which is the subset sum problem, because this problem will entirely be solved with the idea of subset sum. So let's check out the question. So the question says partition a set into two subsets such that the difference of subset sums is minimum. So you're given an array containing n non-negative integers. Again, very important. It has all non-negative integers. Your task is to partition that array into two subsets. So basically subset 1 and subset 2, such that the absolute difference between both of the subset sums is as minimal as possible. Your task is to find the minimum absolute difference considering any valid division of array elements. So let's quickly check out an example. So if we see this example 1, 2, 3, 4, let's discuss over here. So if I take this example 1, 2, 3, 4, what are the different kind of subsets that you can divide it into? So you can say one of the subsets is 1, 2, the other subsets is 3, 4, and the summation of this guy will be 3, and the summation of this guy is 7, and the absolute difference is 7 minus 3, and that's 4. So this can be one of the partitions, or you can say the other partition is 1 3 and 2 4, where you say 1 3 belong to a subset and 2 4 belong to a subset. So the summation is 6 over here and the summation is 4. So 6 minus 4 is equal to 2. Similarly, there can be a lot of different patterns, different partitions rather, not patterns. So I can be like, okay, can I divide this into something where we have 1 and 4, and the other place we have 2 and 3. So again, makes sense. And this time the summation over here will be 5 and the summation over here will be 5. So 5 minus 5 will be 0. And if you carefully see, this is the minimal difference that you can obtain by dividing them into couple of partitions. So in short, you will be given an array. You have to take all the elements and you put some elements in an subset 1 and you put some elements in subset 2, and the subset 1 sum assume it to be sum 1, and the subset 2 sum assume to be sum 2. So the absolute of this is as minimal as possible. This is what the question states. Right now, how do you solve this question? Because this is something different than what we have been doing. What have we done till now? We have done a lecture 14. Yes, we have done a lecture 14. Over there, what have we discussed? We have discussed given an array. Yes, given an array, and I will give you a target, and your task is to tell me if this target, like if there is a subset, if there is a subset whose sum is equal to this target. So you are given an array. We have already done a problem where we have to tell, is there a subset which is equivalent to the given sum target? And if you remember, what concept did we use? We used the concept of pick and non-pick, or take or non-take, the concept that we used. So if you remember the recurrence, it was something like this. We wrote int index, then we wrote the target, then it was something like, if at any moment the target is achieved, we will return a true, and if the index reaches equal to 0, that means basically we started from f of n minus 1 and with the given target, if you remember well, and over here we returned array of 0 is equal to the remaining target, because if we are standing at the last element and some target is yet to be achieved, then the array of 0th index has to have that target. So you remember these were the couple of base cases. Then we wrote a non-take case where it was like we will move to the previous index with a similar target, and similarly we wrote a take case which was initially false, and we can only take the array of index into our subsequence if that's lesser than equal to target, right? And over here we said take will be, if we take it, it's index minus 1 and target minus array of index. So I hope you remember this recurrence. And at the end of the day, we said take and non-take. So that was a quick revision. So we have done this problem, and we will be using this problem's concept only to solve the given problem. So let's forget about the current problem and let's analyze this recurrence relationship. So what did we do on this recurrence relationship? We did apply something as memoization, right? And what after memoization? After memoization, you went on to write the tabulation, if you remember. And how was the tabulation written? The tabulation clearly stated that, hey, listen, if the target is equal to 0, then over here the index can be n minus 1, n minus 2, anything till 0. Basically any index, it can be any index. So we went on to write the tabulation as, firstly though we declared a dp of n of target, and then we went on to write f of index equal to 0 till n minus 1, and over here we went on to write dp of I and every index, rather dp of index and every target 0 as true. So this is what we wrote, because it's almost equivalent to this: if target is 0, return true. So if target is 0 on any given index, you return true. This is the first base case that you wrote. And the next base case was, if index is 0, you are saying this array of 0 to be equal to target. So only at array of 0 you can just write it true, because if the target is equivalent to array of 0, then only it will be true. So if you remember, the next base case was very straightforward. You basically said dp of 0, which is this case, and then array of 0 being equivalent to target. So array of 0 being equivalent to target, which is true. But you just need to make sure, since we are declaring the dp array to be like the second dimension of a parameter target, we just need to make sure this second dimension, yes, has to be lesser than target, has to be lesser than equal to target. Just make sure this condition is written. And yeah, over here it will be of size plus 1, by the way. Perfect. So that was the tabulation. And what after that? You basically wrote couple of loops, which was starting from 1 is to n minus 1. And then you wrote something which started from the target from 0 till, since 0 was already done, you can easily start from 1 till the target k, right? That was it. And you wrote the same thing, not take equal to dp of f of I minus 1. So dp of I minus 1 and target, and the take was initially true. Just making sure if the array of index can be taken into account, which is basically array of I here, if that's equivalent, if that's lesser than target, what you did was you said, by the way, take will be false over here, not true. Take will be false. And you then say take will be dp of I minus 1, and you wrote target minus array of index, right? That is something which you wrote. And at the end of the day, you said dp of I target is equal to take or not take. Similar recurrence I've copy pasted. So this was the tabulation format, right? This was the tabulation format. So what will this tabulation format create? What does a dp of ij signify? That's what my question is to you. What does dp of ij signify? If we are able to figure this out, then that will help us immensely in solving the next problem. So basically, we would have taken something like this. Assume the number of elements to be 5, and the target that we have been asked is 7. Like for an example, let's assume. So can I say we will declare a dp of size 5 crossed 8? So 5 rows is what I'll declare. So let's quickly declare the 5 rows. 0, 1, 2, 3. We have declared the 5 rows. And they'll be like 0, 1, 2, 3, 4, 5, 6, 7. So I'll also declare 8 columns. So kindly declare all the 8 columns. So this is how the DP table is declared. Now, can you tell me, where did you find your answer at the end of the day? You said you call the recurrence, if you remember, you call the recurrence with f of n minus 1 and target. And you said, can an array of n minus 1, like ending at n minus 1, achieve a target? can this entire array achieve this target? That was the stuff. So you also said that the answer will be lying at dp of n minus 1 target. So what does this mean? You are saying for this guy, if n is 5 and the target is 7, you are saying if dp of 4, yes, if dp of 4 and the target is 8, so target is 7 over here, because if you carefully observe, the target is 7. So you're basically saying if this guy is equal to true, then we can have a subset sum of 7, right? So can I say how's the dp array being filled in tabulation form? Firstly, all the base cases are filled. Like all the base cases, what are the base cases? Index equal to something and target true. So firstly, though, you are filling this true, 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 true. That is what you have filled. Now you know that if the array is something like, let's assume the array is, so we know that the array is of 5 elements, right? So assume the array to be something as 1, 3, probably 2, 5 and 6, and the target to be 7. Okay, and the target to be 7. Let's assume this is the array that we have taken and this is the target. So what is the first tabulation that you wrote over here? This is done. And the next thing you're writing is dp of 0, array of 0 is equal to true. So what is array of 0 over here? It is 1. So you placed a true over here. And rest, everything will get filled, 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 filled. Then this will be filled. Then this will be filled. Then this will be filled. Then these guys will be filled. And at the end of the day, this will be filled. And whatever answer is over here, yes, if it is a true or if it is a false, whatever answer is there, you say according to this, I get my answer. That's what you told. But in finding the target equal to 7, if you write the tabulation, you end up filling this guy, because at the index 4, like in the entire array, the target 0 can be achieved. That's very common sense, because if I do not pick up any element in the subset, the target 0 can be achieved. Similarly, whatever value will be here, I can say I can achieve the target 1 or I cannot achieve the target 2. Similarly, whatever value is here, I can say I can achieve the target 1 or I cannot. Similarly, whatever value is here, I can say I can achieve the target 2 or I cannot. Similarly, whatever value is here, I can say I can achieve the target 3 or I cannot. So can I say I can tell yes or no for every target value from 1 to 7? Can I achieve every target value from 1 to 7? I can definitely say yes or no if I write the tabulation, because the tabulation makes sure that I fill the entire matrix, and eventually I will get to know if I can achieve 1, if I can achieve 2, if I can achieve 3, if I can achieve 4, if I can achieve 5, if I can achieve 6, if I can achieve 7. And just because the question asked 7, we picked up this guy and we said this is our answer. Yes, this is our answer, dp of 4 of 7. If the target was like, if someone comes up and gives you a different target, now you still can say without calling the tabulation again. This dp will strictly help you to tell if you can achieve a target 5 or not. So this is what I wanted to portray you. This is what tabulation signifies. For here, 3 means till only the third index, a target of 4 can be achieved or not. Till only the third index, that means till here a target of 4 can be achieved or not. This is signified by the third row. Similarly, every row is signifying something. Make sense? Okay, that does make sense, right? Okay, so we have understood this. So just keep this in your mind that as of now, from subset sum, what we have derived from subset sum, the tabulation one, what have we derived? We can, like, if we check for a target equal to k, we can derive if every possible target, I repeat, if every possible target between 1 and k is possible or is not possible. If I'm just checking for target equal to k, the tabulation automatically will tell me for every value between 1 to k. I don't need to do any extra steps. Make sense? So with the help of this, I'll solve the next problem. Okay, so now let's come back to the DP16, which was the original problem. What did the original problem state? Divide them into couple of subsets, like if one subset is containing some elements, the other elements will be in the other subset. This will have a sum 1, this will have a sum 2. So both of the sums, like absolute difference, should be as minimal as possible. That was the question, right? So we were like, how can we solve this? Because we have just now learned, yes, we have just now learned that we can easily check if any subset of any given sum is possible in an array or not with the use of the matrix, right? So can I say if I can just figure out s1, s2 I don't have to figure out. Think it yourself. I repeat, if I can figure out s1, I don't have to figure out s2. Why? Let's realize. If I give you an array like 3 2 7, okay, and if I say one of the partition contains 3, so the summation is 3. Do I need to find the other partition like 2 7, do the summation as 9? Do I need to do that? The answer to that is no. Why? Because if I know the total sum, because the total sum over here is 12, if I know the total sum, so can I say that if the summation is 3 for the first partition, the summation for the next partition will be total sum, because total sum means all the elements minus the sum of the elements that are in the partition 1. So 12 minus 3 is 9. Again, makes sense, because if the total summation is 12, which is that all the elements, if you take out 3, the remaining elements will be nothing but 12 minus 3. So you get the easy sum of S2. Can I say in this way, can I also say if I take just 2, then it will be 2, which will be S1 will be 2, and the next partition will be 10, like the summation will be 10, because if I take 2, these guys will be in the next partition. Again, makes sense. So can I say what am I looking for? I'm looking for S1 minus S2 to be as minimal as possible. So if I'm looking for S1 minus S2 to be as minimal as possible, do we actually require, yes, do we actually require all the possible, like if I can give you all the possible S1s, then your job is done. If I can give you all the possible S1s, because I can say I'll try out all partitions of S1. You'll be like, but Striver, how's it gonna work? Again, it's gonna work. If I ask you what can be the all the partitions of S1, can I say the minimal summation, the minimal summation of S1 will be 0, where I say I don't pick up any element, where I say I do not pick up any element. Make sense? And the maximum summation will be when I say all the elements are in my partition. Okay, 12. So can I say the minimal value of the partition 1 summation will be 0, where I say none of the elements are in my partition. And the maximum value that I can get, is 12, where I say all the values are in my partition. So I know the minimal value is 0 and the maximal value is 12. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now I ask you, I know the S1 will be in this range, but I need to determine which are the valid S1s, because everyone cannot be S1. All the partitions are not possible. So you'll be like, okay, we remember DP14. Just now I taught you. The last row will tell you if 0 is possible, if 1 is possible, if 2 is possible, if 3 is possible, if 4 is possible, if 5 is possible, if 6 is possible, if 7 is possible. So can I say, I know one thing, 12 is possible because I will take all the elements. So if I call the tabulation method for this, which is size 3 and 12, if I call the tabulation for DP14, the DP14's last row, yes, the DP14's last row will tell me if 0 is possible, 1 is possible, till 12. In that case, it will. So now what I can say is, okay, let's check if 0 is possible. And it will tell me, yes, 0 is possible. Let's check if 1 is possible. It will tell me, no. Let's check if 2 is possible. It will tell me, yes. Why? Because 2 is possible. 3 is possible, yes. 4 is possible, no. 5 is possible, yes, because 3, 2. 6 is possible, no. 7 is possible, yes. 8 is possible, no. 9 is possible because 7, 2. 10 is possible, yes, because 7, 3. 11 is possible. I don't see any way I can make 11. Can I? 7, 3 will be 10. No, I can. 12 is possible. So I figured out what values are possible. And this can easily be done with the help of the last row that has been generated in this DP array. If I call the tabulation method of subset sum. So can I say that 0 is possible, 4 is possible, 6 is possible, 8 is possible, 11 is possible. So these are the valid S1s which are possible. These are the partitions that are possible for S1. So can I find the corresponding S2? Just think inside your brain. Can I find the corresponding S2? And the answer to that will be yes. This will be 12, right? This will be 10, right? This will be 9. This will be 5, 7. This will be 5. This will be 3. This will be 2. This will be 0. So I see that I got, for every S1 I got the corresponding S2. For every S1 I got the corresponding S2. Can I say the difference, the absolute difference over here is 12. Absolute difference over here is 8, 6, 2, 2, 6, 8, 12. What do I need? The minimal. And what's the minimal that I see? It's 2. So that's my answer. Using subset sum, I did it super duper easily. I don't find any problem in this. And this is definitely going to be my answer. Now we can probably write it. Assume you have called the subset sum problem. The DP has been generated. So it's basically, you call the DP for n and summation plus 1. And you can say this is the total summation, because that's the maximum value you can. Call the subset sum code, okay? I'll show you in the code. Call the subset sum code. So the DP of the last row will be right there. So now you can say that I know from 0 till the total sum it is possible. And assume you can keep the mini as 1e9. Can I say if DP of the last row and this target I is possible, then what will be S1? I know S1, like if I just write it, S1 will be I, S2 will be total sum minus I, correct? So thereby I can say minimal, because I need the minimal absolute difference, mini comma absolute of S2 minus S1. So that's how you can easily write this. So if you try to write this in terms of formula, it's going to be total sum minus 2 into I. So you can also write that. But yeah, in this way, if it is possible, if this summation is possible, you directly check on the last row. You take S1, you take S2, and you get the minimal possible value. Now, can we optimize this? Yes. If you carefully observe, 0, 12, 12, 0, 2, 10, 10, 2, 3, 9, 9, 3, 5, 7, 5, 7. So basically what happens is the subsets. So you had 3, 2, 7, right? So first time it might have taken 3 in the subset, in the partition 1. In the next time the partition 1 might have 2. The next time the partition 1 might have 7. Going across, there will be a moment, the partition 2 will be having 3, partition 2 will be having 2, the partition 3 will be having 7. Like it can also have single elements. So do we need to check? Because we're just checking for absolute difference. So thereby I can say, if I check for half of the sum, if I check for the half of the sum, then also we should be good enough, because I know whatever partition 1 looks like, if I make the partition 2 look like the same, the answer is not gonna vary so much. If you carefully observe, we took a summation 0, and going across we set the partition 2 have summation 0. We took a summation 2, going across we set the partition 2 to have a summation 2. So it doesn't really make sense. That's why if you still do till the half, you get your possible answer. So that's how we can easily solve this problem. It's time to show you the code so that it gets much more clear to you. So by the way, this was the lecture 14 subset sum equal to, and this was the entire code. Okay, so what we will do is, let's check out over here what's given, array and n. So at first let's keep a total sum. Okay, let's just keep a total sum as 0, and probably we can just sum it up by going till 0 till n, which is I plus plus, and I can say total sum is equal to array of I. That's something which we will do, right? Right after this, what you will do is, you'll just call this guy, nothing else, just call this, just copy paste, because this is the subset sum, and this is the n into k plus 1 vector. So instead of k, k will be the target over here is initially total sum, because that's the maximum that's possible. And yeah, there was the edge case that was missing over here. The array of 0 has to be lesser than equal to the target that you're looking for, otherwise it will overflow. So just make sure you do this, the array of 0. So I can say the entire vector is generated, and over here can I see the array of, or rather the dp of n minus 1, and the entire column from 0 to the total sum will tell you the answer. I can, so I know I need the minimal, so minimal can be 189, and I know I can start the target, like I can start the s1 rather from 0, and the s1 can go on till total sum by 2, that we have already proved that, and s1 plus plus. So can I say this, if dp of the last row, in the last row, if s1 is true, then only it's possible, then only it will be possible. And if it is possible, can I say mini will be min of mini comma total sum minus s1 is what your s2 will be, minus of s1, and an absolute of the entire stuff. Yes, an absolute of the entire stuff. And at the end of the day, can I say I will return the mini? So if I just write this, and let's run this off, and let's see if it's running fine. It does run. So let's quickly submit this off. So you see, it is running absolutely fine. Did we do anything extra? Just these couple of lines and just a total summation that I did. Apart from that, the entire concept of subset sum was used. So if you remember, in subset sum we did a space optimization, so you can do a space optimization over here as well. So what I'll do is, I'll just copy paste the space optimization code. This is the space optimization code. So let's quickly take this off and copy paste. We'll copy paste the space optimization code. So instead of dp of n minus 1, this will be previous, because in space optimization this is what we usually do. So let's quickly now run this off. You can also try it with the space optimization, that's your choice. So if you do the space optimization, it will take a bit lesser space complexity, but the time complexity still will be equivalent to n into target plus total sum by 2 plus a big O of n linear loop. So a couple of linear loops and the total sum n into k, and the time space complexity will be big O of these guys. That's a single linear loop that you single linear array that you're using. So guys, I hope I was able to make this tough problem easy, and just in case I was able to make it, please like this video, because I'm recording this at 5 AM in the morning, and yeah, I'll be editing it for the next 1 hour. This video will go tomorrow morning. So yeah, just make sure you like this video, and if you're new to this channel, please do consider subscribing, and in the comment section, please do write understood if you have understood, because that does motivate me a lot. And yeah, with this, I'll be wrapping up this video. Let's meet in the next lecture. Till then, bye bye, take care.
Whenever your heart is broken, don't ever forget you're golden.